Hi everyone, my name is Dilrukshi. I'm going to present the paper Laboratory Testing to Calibrate Discrete element models simulating the effect of particle size on soil behavior. The research was done at University of British Columbia by myself, Judy May, under the supervision of Professor Wijewickreme. So let me start with the background to this research. At UBC, we conduct a lot of research on soil pipe interaction and integrity of buried pipelines. In one of the research we conducted at UBC Advanced Soil Pipe Interaction Experimental Facility, we noted that relative bacterial particle size with respect to the pipe size may influence in controlling the lateral soil restraint of buried pipelines. What we noted was when pipes buried in uniform, significantly coarse-grained soil bacteria subjected to relative movements, the bacterial mass disintegrate and flows at individual particles, leading to post-peak reduction of soil restraints. So we decided to further study on this matter. However, conducting experiments was not an option. They're expensive and time-consuming. Therefore, we decided to use a numerical approach. However, we had two challenges. So we needed to study the effect of particle size, and also we needed to model the flow of individual particles. So continuum modeling was not an option. So therefore, we decided to use discrete element modeling. As you all know, the discrete element technique allows to model granular materials as collection of separate particles. So in turn, it would provide us an insight into relation of particle scale interaction and overall material strength. Therefore, well suited for this study. So in the discrete environment modeling, the contact between the particles is generally modeled through the normal stiffness, shear stiffness, and the friction coefficient between the particles. Therefore, model calibration is very important in discrete element modeling to decide these parameters. So often done through laboratory element testing and equivalency in simulation because they are not measurable parameters. In our soil pipe interaction research, objective was to study the effect of particle size. Therefore, we conducted this particular study in the objective to determine the effect of particle size on calibrated discrete element model stiffness microparameters. And we found that one-dimensional compression testing is particularly suited for calibrating particle stiffness material parameters, and therefore we use that approach. So our approach was very simple. We designed simple one-dimensional compression testing setup, and we use glass beads as our material. It's because of the shape of the glass bead, spherical and known parameter, it was easy for us to re-simulate them numerically. For the numerical simulations, we use commercially available particle flow code software, EFC3D, and we use both linear contact model, which uses the stiffness microparameters as the direct input, as well as the Hertz-Minton contact model, which calculate the stiffness between particles based on the particle size, material properties, and the overlap between the particles to simulate our models. So approach was simple. So what we did was we changed the numerical model parameters until we get a good match between the experimental and numerical output. So when I'm talking about the output here, what I was talking about is, as you all know, in the axial stress strain plot, stiffness is given by the gradient of the curve. So we change our parameters until we obtain the same gradient we obtained from the experimental results. So these plots compare the results between the experimental and numerical simulations for different particle size and using different approaches. As you see, Hertz Middleton contact model has a good ability of reproducing the experimental results. The reason was, at the beginning of the experiment, the spherical particles try to rearrange and come to a stable position before they are subject to compressive testing. So Hertz-Middleton contact model is able to capture this effect very well than the linear monochronic. That's why we see a small difference here. However, both approach was able to capture the stiffness values we obtained during the experiments. Then, when we have the parameters, then we try to obtain a relationship between these individual particle stiffness parameters and the material parameters. So since we use one-dimensional compressive testing, we decide to compare our results with the tangential constraint modulus values of the material. Our approach was simple. We use hyperbolic restraint model and curve fitting to obtain the relationship between the particle stiffness and the average constraint modulus. However, we call this relationship is preliminary because we only have three data points. And so in order to use this equation in long term for modeling, so it is necessary to conduct more studies to validate this relationship between the average constraint modulus of particle stiffness. But as for the overall conclusion of the study, the results suggested that particle stiffness microparameter increases with the particle size. And for our study of 1 millimeter and 9 meter glass piece, we found a increased factor of 14 between the parameters. So we derived the preliminary relationship. However, it's necessary to conduct further studies to confirm this relationship or to use that equation. But in overall sense, the findings suggested that particle stiffness microparameters should be carefully selected to represent the particle size, effect in the EM simulations, and in turn, be utilizing quantitative analysis of geotechnical engineering problems. In most cases, discrete element modeling is used to study the qualitative behavior, but if you are going to use quantitative analysis, it's very important to study or to find or use the approach to capture the effect of particle size in overall. Thank you very much for listening. If you have any questions, please send those questions to us. Thank you.